It's recording.
Okay.
And then on top is typing right for the system.
All right, so let's see. First of all, we're going to have a midterm after fall break. I asked students to send me email as to whether they want on Tuesday or Thursday. I got 3 or 4 emails saying Thursday. Nobody wanted Tuesday. So does anybody want Tuesday, or should we do?
It's not a strong preference with my Thursdays.
You have no preference?
I prefer Tuesdays because my Thursdays are kind of insane, but it's fine.
Well, does anybody else want Tuesday? All right, so let's say Thursday, just regular class time. Oh, here, let me give the videographer some. Would you like candy or not?
Sure. Thank you.
So the TA told me that I was assigning too much homework, or he thought I might be, so I cut back and I made the last 4 problems or so extra credit in the assignment that's due on the 27th, which I think is this Friday. The next 2 assignments are 9 problems each, as opposed to 14 or 15 problems. But I need feedback from you guys to tell me if you think I'm assigning too much homework. You've got to say so, and I can cut back, because I'm not good at reading minds. And I also, if you would ask more questions in class or come see me more often in my office and ask questions about the material, or ask to see the homework problems and then ask me to explain some of the solutions to some of the homework problems, then I would have a better idea of what it is that you know and how well you're understanding what I'm teaching and whether I'm going too fast or too slow. I do manage to avoid grading too harshly, but sometimes I may teach too thoroughly. I, of course, want you to know everything that's in my book, or at least the first half of the book. And of course, I think it would do you good in future work, whether you become an experimentalist or a theorist, or you switch into medicine and earn real money. All right. Now, I'm of 2 minds as to whether you're better off when I lecture on the screen or whether when I write on the blackboard. The advantage of using the screen is that I can go faster, but that may be for you a disadvantage. I'm thinking that maybe the best thing is for me to do 1 more lecture today using the computer as a projector, and then I'd ask you guys to send me emails saying, do you prefer me to write on the board or do you prefer the overhead projector? I'm pretty much recovered from the hospital experience, and so I can write on the board certainly next week, but even today. Does anybody have a strong opinion right now? All right. All right, so let me do another sit-down overhead projection one. And what I'm going to try to do now is start by covering quickly the rest of the material in let's see, how do I want to make this bigger. So I'm thinking of covering the material in most people missed class in which I did most of chapter 4, so I thought I'd review that material quickly as far as I got, and then slow down and show you in more detail. Let's see, are you by any chance Mallory Harris?
I am. Unless somebody has a strong objection, we're going to have the midterm on Thursday after fall break. Okay.
Do you strongly prefer Tuesday?
No. I'm fine with Thursday.
I want you to think of the exam as an opportunity to review the material and to learn it better. And as I've said to you before, I tend to grade generously, but sometimes I try to teach too much. So let me just review. These are the Fourier Transform formulas that we learned about in chapter 3. And the procedure here is to change this index n into a continuous variable y. And so I'm writing f hat of y is going to be f sub n, with the understanding that the way we do that is we say f hat of y is f sub y inside these square brackets, and these square brackets mean the nearest integer to the real number y. This is one of the standard notations. Square bracket y is, if y is 2.1, square bracket y is 2. If y is 2.9, square bracket y is 3. And so then we can take this expression here and we rewrite it this way as just an integral over this function as over a continuous variable from n minus a half to n plus a half, and this just reproduces that. And then if we combine all these integrals as represented by the sum, we get just an integral from minus infinity to plus infinity of the continuous variable y. The next step is a bunch of change of variables, and in the change of variables, you see we're going to the limit where L, capital L, goes to infinity. When L goes to infinity, the difference between the real number y and the greatest integer nearest that real number y is small compared to big L, because big L is going to infinity. And so we can just replace the nearest integer to y by y. And when we do that, we've written f of x as essentially a Fourier transform. We make a few more changes of variables, and we actually get the Fourier transform formulas here. So you should read over this material and understand it well. And as I said, or as it's written here in the book, whether you use a plus here or a minus, if you use a plus, you use a minus there. If you use a minus here, you use a plus there. If you don't have a 2 pi here, you have to have a whole, if you don't have a root 2 pi here, you have a 2 pi there, and so forth. Let me just mention briefly that the Fourier transform of Gaussian is a Gaussian, and in tomorrow's problem session, I'm happy to do in detail any of the examples that you may want to see, and I can also discuss homework problems if that's what you'd like to see. But anyway, the Fourier transform of a Gaussian is a Gaussian, and the one interesting thing to keep in mind about that is that if the Gaussian is e to the minus m squared x squared, then the Fourier transform is e to the minus k squared over 4m squared. So in other words, suppose m is very small, then this thing decreases very slowly and it extends way out to large values of x because m is small. But if m is small, this decreases very rapidly, and so the function, the Fourier transform of a slowly varying function is peaked, and vice versa. So there are these complementary relationships between a function in space and momentum space, or Fourier transform space. Remember, you ask questions, you learn things, and you get candy. Also, if you ask questions, I get a better idea of how fast to teach. Fourier transforms of real functions, you take the complex conjugate, you just flip this minus I to plus I, but f doesn't change. But this is the formula for f tilde minus k, so you have the relation that f tilde of k is f tilde of minus k if the function is real. Okay, so these are various examples that are of some importance. Now, as I've said to you many times, Dirac's contributions to mathematical physics are really, have been immense, and in particular, his Dirac delta function and his Dirac notation for bras and kets are a big help to graduate students and working physicists. So let's just look at the Fourier transform relations from the point of view of Dirac for a moment. Then you write the function f of x as its Fourier transform in terms of the Fourier transform and this integral over k. But now you can write the Fourier transform as the inverse Fourier transform, which is one of the relations we derived quickly earlier today. And when you do that, you get this double integral. If you now combine the two, you see that f of x is this double integral f of y. That means, well, let's compare this equation with the equation for a Dirac delta function, which is that if you integrate the delta function of x minus y times f of y, you get f of x. On the other hand, combining these two, we see that if you integrate f of y times this thing in parenthesis, you get f of x. So that means this thing in parenthesis is really a delta function. And I then showed you that graphically by taking capital N to be 10 to the 6 or a million, and did this MATLAB computation where the bottom here is 1 part or 2 parts in 1,000, and this is 10 to the 3 parts or nearly 4 parts in 10 to the 5th. So this shows you that that Dirac delta function formula is real. It's not some mathematical fiction. It's actually something that MATLAB produces. And you remember many times I emphasized that the identity operator could be written as an outer product of bras and kets, and that if you did that, you were able to derive all kinds of relations that are important in linear algebra, and especially in quantum mechanics. Well, the same is true if you take this thing, because this thing is saying that this integral here is the identity operator in function space. And so if we rewrite it this way, we can write f of x as an integral dy of effectively this is in essentially if you think of f as a vector with continuously infinitely many components, then this says the vector is the identity operator times the vector, so matrix multiplication there. Well, you rewrite the Dirac's delta function like this, and it becomes this. You then do the y integration. Well, the y integration gives you f tilde of k. And so this y integration with f of y e to the minus I ky, that gives you f tilde of k, and what you're left with is, well, you needed a square root of 2 pi. You're left with the square root of 2 pi under a dk. You have e to the I kx f tilde of k equals f of x. So you see, this expression for the Dirac delta function gives you directly the Fourier transform relation, which is this on the left-hand side. So that's just another example of how extremely useful Dirac's notation and Dirac's ideas are in mathematical physics. The inner product of two functions is the integral of the complex conjugate of one times the other. And if you write them both in terms of their Fourier transforms, and then use this integral as a, realize that an integral over x of this thing here is delta of k prime minus k, that gives you that the inner product is not simply an integral of f star of x, g of x, but it's also an integral of the complex conjugate of the Fourier transform of f times the Fourier transform of g. And so that means that the Fourier transform maps inner products in Fourier space into inner products in position space, and so the Fourier transform is unitary. The Fourier transform also has the marvelous property that for square integrable functions, it's one-to-one and invertible. And that's really, that's the gold standard for a transformation. And one other thing about delta functions is in physics classes very often, math classes not, but in physics classes you wind up with delta functions of complicated arguments. You need to know how to deal with them. Well, let's consider the case where g of x is 0 only at one point. When g of x is not 0, the delta function ignores it and maps that part of the integral to 0. So suppose the point is x0. G of x0 is 0, but the derivative of g at x0 is not 0, and g at x is not 0 when x is not x0. Then we can pull out f of x0, and we're left just with this. The next thing we can do is write g of x as x minus x0 times g prime of x0. And then we can multiply both sides by the absolute value of g prime of x0. This then becomes dg. This is dg. And so what we've got is an integral dg, delta of g minus g0 times this in front. This just integrates to 1 because that's what delta functions do. And so that's the answer. So the upshot is the delta of g of x is delta of x minus the value of x that makes g 0, and it's divided by the absolute value of the derivative of g at that value of x0. If g happens to have several zeros, then you just repeat the thing for each 0, and you get a sum on the right-hand side. So delta of g of x is a sum over the various zeros of g of x of delta functions divided by the absolute value of the derivative of g at those roots of the function g. All right, I think we can skip that, but if you read it, that is useful. You remember we had a formula for what is called the Dirac cone, which is really this rather magical Fourier relation between a sum of Fourier factors and a sum of delta functions. You multiply it by a function, you get this expression, and that gives you that. This here gives you the Fourier series values, and this gives you the value of the function. And so that tells you that the actually, that what I said Fourier series, these are actually Fourier transform values at integral values of the argument n. And so the Fourier transform at integral values is summed, apart from a factor, is equal to the sum of the function evaluated at 2 pi L for all integers. This is a useful way of approximating some functions, because typically one side will converge slowly and the other side quickly, and so you want to use the side that converges quickly. All right, let me skip that. Derivatives and integrals of Fourier transforms. Well, you know that differentiating and integrating exponentials is very easy, and so if you have an expression for a Fourier transform, you differentiate with respect to x, all you have to do is differentiate this phase factor, and that pulls down an ik. And if you do it twice, you get ik squared, which is minus k squared. You do it n times, you get ik to the n. So Fourier transforms, apart from all their other uses, they make differentiation trivial. They also make integration trivial, because if you integrate a phase factor, you just divide by ik for the indefinite integral. And so you indefinitely integrate n times, which I'm using this non-standard notation. I don't know, maybe one of you knows a better notation. If so, speak up. Anyway, I invented this notation. I suppose it's in use somewhere. Anyway, the nth indefinite integral of the function f of x has as its Fourier transform the ordinary Fourier transform divided by ik to the n. And which one converges better depends upon whether f tilde of k is how it behaves at 0 and infinity. Here are some examples of the use of Fourier transforms in physics, and I urge you to study them, especially if quantum mechanics is new to you, then you should absolutely study these examples. Here's the uncertainty principle derived. The mean value of an operator is in terms of a density operator, is written this way. And for example, for the mean value of a position operator, you get that. The variance of an operator is given by, in quantum mechanics, it's the mean value of the difference between the operator and its mean value squared, and it's the mean value of that thing. Or for a density operator, it's this. Anyway, that allows you to derive the Heisenberg uncertainty relation. I don't know if I told you, but I once met Heisenberg, actually, at Berkeley, years ago, obviously. We didn't do more than shake hands, though. The characteristic function, I will mention this example a little bit because it's used in, you need it for one of the homework problems or two of them. If you have a probability distribution, typically integrates to 1. The Fourier transform of the probability distribution is called the characteristic function. That's simply the definition. The expected value or the mean value of a function is the integral of the function weighted by the probability distribution. The characteristic function itself can be thought of as the expected value or the mean value of the phase factor e to the I kx. And its derivatives at k equals 0 are the moments of the probability distribution. So the mean value of x to the n is, of course, x to the n times the probability distribution integrated over x. Well, if you use what we just learned about differentiating Fourier transforms, you see that is just the kth derivative of the characteristic function apart from a factor. And this is discussed further in chapter 15, which is about probability. Okay, Fourier transforms of several variables. You just repeat what you have for one variable. And in fact, you can also use Dirac's delta function twice, and so forth. If you want to have the Fourier transform of n variables, you just do what you did for one variable n times, and so you have n square roots of 2 pi. And the relationship between Fourier series and Fourier transforms, that looks like this. And in particular, in 3 dimensions, it looks like this. This is a useful expression because sometimes in a physics problem, you'll know what the Fourier transform is, but you'll need the Fourier series, or you'll know the Fourier series and you need the Fourier transform. You can go from one to the other. The definition of a convolution, it has this rather bizarre and off-putting notation, f star g of x, and it's the integral of f of x minus y times g of y integrated over y divided by a square root of 2 pi. It's symmetric, and you can see it's symmetric just by writing it out and then changing variables, letting z equal x minus y, keeping track of the rules for integration, and you get this, which is just the definition of g star f of x. So, as I said to you, the convolutions look strange if you've never seen them in print before or verbally. But you've seen them in physics classes in this form. For example, the potential is an integral of sort of 1 over x minus x prime times the charge distribution. That sort of thing. And this occurs all the time. That's explained in this example, and I'll be happy to do this example if you want tomorrow in the problem session. The thing that mediates between the source of the this you can think of as the source of the convolution and the effect of the convolution. This is often called a Green's function, named after George Green. Here are some more examples of this, and the magnetic vector potential. Here's another example. This is a magnetostatics. The vector potential is proportional to the current distribution divided by x minus x prime. Okay. As I said, Fourier transforms, they're just marvelous things because they just have all these magical, nice properties. In particular, the Fourier transform of a convolution is the product of the Fourier transforms. And in order to see that, all you do is write the thing out. The Fourier transform of the convolution, well, it's the Fourier transform of the convolution. You then write the convolution as its definition, and then you write each of these functions in terms of its or their Fourier transforms, and you get this huge expression. Now, without Dirac, this would be hopeless, but with Dirac's delta function, this thing collapses like a house of cards, and you just get that the Fourier transform of a convolution is the product of Fourier transforms. So once again, I just can't emphasize strongly enough how useful Dirac's insights into mathematics are for physics graduate students. They make your life so much easier. Now, Fourier transforms and Green's functions. I mentioned Green's functions earlier as the thing that occurs in a convolution. You can also think of them, and in fact most people think of them as, well, I shouldn't say most people, but another way of thinking of a Green's function is it's the thing that takes a differential operator. It's the thing that when operated on by an operator like a differential operator gives you a delta function. And the reason that you want a Green's function is that if you know what G is, you can then solve equations that involve P of a polynomial and derivatives. Of course, equations that involve polynomials and derivatives and don't involve x, in other words, P here is a function of derivatives, it's not a function of x1 or x2, it's just a differential operator. So that means that its differential equation is simpler than a general differential equation. But in any event, if we try to find G, the way we do that is we say PG is, well, we write G in terms of its Fourier transform. So that's G tilde, and it's e to the I kx, and it's an n-dimensional Fourier transform. I left out the 2 pi's here, I don't know, to make the notation simpler. But on the right-hand side, we want the n-dimensional delta function. The n-dimensional delta function is just Dirac's formula written n times, so it's this. And in fact, the reason I wrote the 2 pi's this way is that Dirac's delta function has the full 2 pi in the denominator. So this gives you an algebraic equation. It's that the Fourier transform, this is a Fourier, this says that the, oh, how shall I say this? The point is that these functions, e to the I kx, are independent functions. And consequently, if you have an integral over them on one side equals the integral over them on the other side, you can equate the coefficients. So you can say that PG is equal to 1 over 2 pi to the n. So the Fourier transform of the Green's function is 1 over 2 pi to the n, P of ik. So the Green's function for this differential operator is an integral over all k divided by 2 pi to the n e to the ik dot x divided by P of ik. So P is a polynomial originally a polynomial in differential operators. Here it's a polynomial in ik, and this gives us the answer. And in particular, if you apply that to equations that occur in mathematical physics, like minus grad squared plus m squared on the Green's function equal delta, what you get is the Yukawa potential. That's the Green's function for this differential operator. Any questions? I've covered a lot of material here. Laplace transforms. Well, although Fourier transforms can represent any square integrable function, they're not good for functions that aren't square integrable or functions that aren't integrable. That, however, you can use the Laplace transform. And the reason is that Laplace transform is kind of a Fourier transform at imaginary k, and so you have this convergent factor, e to the minus st, and you only integrate over positive t. So f of t can be as big as a growing exponential, and you still get a reasonable Laplace transform. So that's the advantage of Laplace transforms. In particular, the function 1 is not square integrable. Its Laplace transform is just 1 over s. The function e to the kt is not square integrable, especially if k is real. You integrate it, you get e to the minus s minus kt. The answer is 1 over s minus k. No problem. You apply these tricks to these various functions, which of course are sums of exponentials, and you just operate, you just do these 8 integrations and you get these expressions. So these formulas illustrate that all sorts of non-integrable functions have very nice Laplace transforms. Here's a biophysics example that's worth looking at. Biophysics, as I mentioned on Thursday, is a field that I keep recommending to physics graduate students because it's a field with millions of jobs that are high-paying. You can get a PhD here in biophysics, and your first year out, you're making more than I make. Okay. So biophysics is a good field. Not only that, but if you get a PhD in physics here in some fields, you might wind up working for a company that makes weapons of mass destruction. You know, how can you sleep at night? Well, if you major in biophysics, later on you'll make more money and you'll be advancing the field of medicine. You may be saving people's lives. I recommend biophysics. We have a small biophysics group now, Keith Lidke and Jim Thomas. We're going to hire somebody else shortly. And, our people are quite good. And in particular, Keith's people, when I say these guys are earning more than I am, I know for a fact that Keith's graduates are all making more than I make. So, and it's also very interesting work because you learn a whole other field of science to go with your physics. You learn molecular biology, which you can pick up on the you sort of pick up on the street, molecular biology. Compared to theoretical physics, compared to my course, molecular biology is child's play. And as I say, you can just, there's a book, it's a marvelous book. It's one of the best textbooks ever written. It's called Molecular Biology of the Cell. It's in its 6th or 7th edition. And you can buy that book or download it or steal it or something and get an electronic copy and read it. It reads like a novel, but a very good novel. And if you read the whole book, you essentially have the equivalent of the theoretical understanding of a bachelor's degree in biology, at least for molecular biology. All right, just enough of the biology commercial. Just as derivatives and integrals of Fourier transform are easy to do, so too for Laplace transforms. They're also easy, and for the same reason, the Laplace transform essentially is an integral of an exponential. And so when you differentiate a Laplace transform, you just pull down, you just differentiate e minus st, and you pull down minus t to the n. And so for example, if f is 1 over s, if the Laplace transform 1 over s, you differentiate n terms, you get this, and that gives you a new Laplace transform relation. You find the Laplace transform t to the n is n factorial over s to the n plus 1. Notice again, t to the n is not an integrable function, so it doesn't have a Fourier transform, but it has a Laplace transform. You can also integrate easily, but this is trickier. Suppose you consider the Laplace transform the integral of f. Well, then if you integrate by parts, you assume that f, although might be not integrable, you assume it's 0 at infinity, then you get this expression. Well, actually, you don't even need to assume that f is 0 to infinity, because you see f is multiplied by e to the minus st, and t is going to infinity. So you don't really need to assume very much. So you get minus f of 0 times this, but on the other hand, this is the Laplace transform of, this is s times f of s. You can just pull out the s, in other words. And the integral dt f of t to the minus st is f of s. So this is a relation then that is used in the theory of differential equations. And in particular, the integral of the Laplace transform is then, well, you just integrate the e to the minus st and you divide by that, you do it n times and you get this. And if f of s is well behaved, these are usually well defined for positive s. Okay, any questions? All right, so let me mention then something about Laplace transforms and differential equations. This is essentially a repeat of what I just said about Fourier transforms and differential equations. So here we have a differential operator, let's say a polynomial. Because I said this was a polynomial, it doesn't have to be a polynomial. It just has to be a function of only of the derivatives. Acting on f gives you a source function. So this is a species of Green's function here. What you do is you write f and j as their Laplace transforms, and then you get this expression. P of d by ds on f of s is e to the minus st, p of minus t, because when p hits e to the minus st, it turns it into p of minus t. And the right-hand side, j, is just the integral of its Laplace transform. So now, keeping in mind that, you then just say, well, if you want this to equal that, you better have pf equal j, or f is j over p of minus t. So that tells you then that the solution, f of s, is the Laplace transform of the ratio j of t over p of minus t. Well, p of minus t is trivial to calculate, but j of t is not trivial, because in order to get j of t, you have to be able to find the, I guess, inverse Laplace transform of j of s. In other words, what function j of t has as its Laplace transform j of s. So you have to invert a Laplace transform. But before getting to that problem, notice that we physicists often are happy when we get to this stage, because we sort of feel in our bones that you don't get nothing for nothing, and so, except in chaotic inflation, and so we generally don't knock ourselves out about this equation unless we're forced to. But in fact, mathematically, whenever we solve an inhomogeneous equation, we have to realize that the general solution to this equation is the solution to the inhomogeneous equation plus a general solution to the homogeneous equation. The homogeneous equation being PF equals 0. So to find the solution PF equals 0, what we do is we just use, once again, we lean on Dirac, and we just pick an arbitrary function h, and we multiply it by delta of p of minus t, because then, and we say this is our homogeneous solution, because then when p hits f, it pulls down p of minus t. But this equation then is an integral over t of p of minus t delta p of minus t. But delta is non-zero only when p is 0, but then the integral is 0 because the delta function gives us e to the minus st times 0 times h, so we get 0. So the actual general solution then is the solution to this solution to the inhomogeneous equation plus this general solution to the homogeneous equation. Now, as I said, in order to implement this that technique, you need to be able to invert a Laplace transform. Inverting a Fourier transform is just doing a Fourier transform. Of course, that's not trivial either, but it's more straightforward. Now, how do you invert a Fourier transform? Well, let's write the Fourier transform according to its definition, and we want to find this f of t. Once again, Dirac comes to the rescue. What we do is we extend s to a complex value, s plus iu. And the next thing we do is we choose s to be sufficiently positive that we can integrate over u. In fact, integrate over u, effectively doing a Fourier transform, and not get nonsense. So in other words, by what we know here is that f of s, the bigger s is, the more well-behaved, the smoother and the smaller f of s is, because this e to the minus st dampens f of s as s goes to infinity. So we push s out as far as we need to until this is a nice convergent integral over until f of s is so small that f of s plus iu is small, and this integral converges. And now we write f of s plus iu in terms of its Laplace transform, or its sort of Laplace Fourier transform, like this, and then we examine this integral over u. Well, we see once again Dirac comes to the rescue with his delta function. And so what we've got left here is dt prime e minus st prime. The function we want, f of t prime times a delta function. Bingo, it's e to the minus st f of t. So now we've got the answer. The answer is f of t is e to the st times this, which is just a du integral e to the I ut f of s plus iu, but evaluated at an s big enough so this converges. So that's our formula. It's really an infinite set of equivalent formulas for the Laplace transform of f of s. This formula is called a Bromwich integral or a Fourier-Mellon integral. So, any questions? Is anybody, has anybody missed lunch and needs a sugar fix? I've got this candy here, I can throw somebody a candy. All right. Okay, let's apply some of this to differential equations. And so this of course is important in physics. So once again, this is a simple differential equation, although it's an inhomogeneous differential equation. Inhomogeneous because there's a right-hand side. So we're asking ourselves, what function gives us g when acted upon by p, where p is a polynomial in the derivatives. I kept saying it's a polynomial, but it really could have been any function. I don't think there's any reason why it has to be a polynomial, actually. Anyway, in fact, I should change that. So, first of all, notice that if G happens to be 0, then we've got a homogeneous equation. And so let's do the homogeneous one first this time. And the reason for that is that many of the equations of physics, and in particular many of Maxwell's equations, are the form some differential operator times the electromagnetic field or the vector potential gives you 0. Anyhow, so what we do to solve this for the, well, for the inhomogeneous case, actually I'm doing the inhomogeneous case, we write f and g both as integral transforms, and I'm saying here that these could be Fourier or Laplace transforms according to how the integral goes. If the integral goes over real k from minus infinity to plus infinity, it's a Fourier transform. If it goes over imaginary k from 0 to plus infinity, it's a Laplace transform. And what we do is we write them this way, and then we use whichever one suits us. And how will we know? Once again, Dirac will tell us. It's just absolutely amazing how many things he invented. I mean, apart from giving us the exact solution to the relativistic hydrogen atom, the Dirac equation, the Dirac magnetic monopole, is just no end. He actually was also working on things that are kind of related to string theory. And he was doing that back in the 60s. Anyway, as I said, you can differentiate these exponentials easily, so the jth derivative, the derivative with respect to the xj m times just gives you I kj to the nth power. And so p acting on f just gives you p, it gives you the Fourier-Laplace transform integrated, and p just picks up I k1 through kn. And we're writing that, of course, in terms of the Fourier-Laplace transform with g. And so this inhomogeneous equation in k-space is an algebraic equation, and so it's pf tilde is g tilde, and so the inhomogeneous solution, or the solution to the inhomogeneous equation is, I means inhomogeneous here, f sub I is the integral over k's of just the ratio of g tilde over p. And so that's just very easy to do, and that gets you a long way in many physics courses. The space of the solutions to the homogeneous equation, where we want p f homogeneous to be 0, and so one way to do that is to arrange that replace g tilde by 0, so we have p of ik f homogeneous tilde of k equals 0. One way to do that is to write the homogeneous one as delta of p of ik times h of k, where h of k is arbitrary. And for that reason, the homogeneous solution looks like this. So when you hit the homogeneous solution with p of the derivatives, that pulls down p of ik, so you have p of ik delta p of ik, that's 0. That's like x delta of x. That gives you 0 in an integral. And so the general solution then is the inhomogeneous plus the homogeneous, and it's this expression here. So this gives you a solution to a whole raft, a whole class of inhomogeneous or homogeneous differential equations. And the wave equation and the diffusion equation are examples. we've got some time, so maybe I will do these examples in detail. And you might say, well, why do you need this stuff? Well, here, this is the wave equation for a scalar field of mass m. Well, if you're going to study optics, you're going to be studying an equation very much like this, but for m equals 0. And instead of one equation here, you're going to have 4 of them, because there are 4 components to the vector potential in electrodynamics. In natural units, one sets h bar and c equal to 1. Natural units are very convenient, because when you set h bar and c equal to 1, you no longer make mistakes with where you put your h. You no longer need to remember to put in h bar and c, and so you never put in too many or too few factors of h bar and c. So your equations are much easier to write. When I wrote this book in the relativity section and in the electrodynamics section, I didn't use natural units. I thought the students would be better off seeing the C's or the H bars in some cases. So I put in the H bars and C's and used MKS units, and it nearly drove me crazy. In particular, I had a lot of trouble finding any book to look at to check my work. But anyway, I hope I got most of them right. So what we do is to solve this, we just write it as a Fourier or Fourier-Laplace transform. Here we're going to get away with a Fourier transform. But it's a homogeneous equation in this case. So we have the equation that this is our relativistic wave equation, and for mass m hitting a scalar field in this case. So when it goes into Fourier space, it pulls down k's like this, and we have that equal to 0. So our algebraic equation looks like this. Well, the way we solve that is we write phi as a delta function of this times essentially an arbitrary function h. And now, this, you notice, is a delta function of a more complicated argument than just something that's linear. And that argument is, in fact, p of ik, namely k0 squared minus k squared minus m squared, which is this thing. And this has 2 zeros at these plus or minus omega k. Its derivatives have the 2 omega k as the absolute value. And so if you use the rule that we looked at earlier for evaluating the delta function of a more complicated argument, we apply that to this case, we get this expression for a scalar field as an integral over 3-dimensional k of these phase factors times functions of 3-dimensional k. And this 2k is the absolute value of the derivative of the argument of the delta function. So the field looks like this, and what one does, classically, your electromagnetic field you can write this way. In quantum field theory or in quantum electrodynamics, you write the h plus. First of all, you realize that your field here is real, and so h minus of minus k is h plus of k star. And or if your field is Hermitian, as it would be in quantum electrodynamics, you get this. You have h minus of minus k is h plus adjoint of k. And then you have this expression where this is an annihilation operator, this is a creation operator. If phi is a scalar field, like a Higgs field, this is the annihilation operator for the Higgs boson, or the creation operator for a Higgs boson. In the case, of course, the real Higgs boson has 4 components, but never mind, and it's 2 complex components, but never mind that for the moment. Physically, there's just one neutral real component. in the case of quantum electrodynamics, you have 4 fields here, and you have 2, although you have 4 fields, you have two annihilation operators for each momentum and 2 creation operators for each momentum. That's because the electromagnetic field, although it has 4 components, there are only 2 polarizations. There's 2, and you can think of them as right and left circular polarization, or you can take linear combinations of those and you get linear and elliptical and so forth. I think we can skip the rest of this, but if those of you interested in quantum field theory should read it. Suppose you want to go from the Fourier transform from a scalar field to a Fourier series. You apply the rules that we looked at earlier, and, or actually I think today I skipped them. I did go through them on Thursday. They're in the early sections of this chapter. You then write the function of the field as a sum over k, and your factors then are written in terms of the Fourier transform variable, but on discrete values, and these of the Fourier transform, discrete values of k, and in fact the k values are typically 2 pi over L, integer values ln m, and the relationship between the annihilation operators is this, and so whereas the annihilation creation operators for crystals or for photons in a laser with a finite box are delta of k minus k prime, so forth. Diffusion provides another example of all these techniques, and in particular, there's a certain amount of biophysics in this example that's very easy for you to learn. Shows you how easy biophysics is. Something called Fick's law is that the flow rate is proportional to the gradient of the concentration. Well, that's what you would guess as the plausible answer, apart from a minus sign and an overall constant called the diffusion constant. And the number of particles, and these things could be bacteria, they could be viruses, they could be molecules, is conserved, well, at least finite time scales. You can then write the time derivative of the integral. That'll be the flow of the current of these things across the surface. You use Stokes' theorem to get a divergence, and then you get this differential equation with the time derivative of the density is minus the divergence of the gradient, and on the other hand, Fick's law said that the flow is minus d times the gradient, so that pops back the density, and so the time derivative of the density is d times the square of the gradient of the density, and so you get this wave equation for the density for things in solution. This is diffusion, and I think this, Roy Glauber once told me that this is what Fourier was working on when he invented the Fourier Transform. And so now let's solve this equation using the techniques that we just learned. What you do is you write this as a Fourier-Laplace transform without prejudice as to whether k and omega are real or not. And then you operate from the left with the differential operator, and you get this expression here, and this again is a homogeneous equation. So this is the easier case. And your algebraic equation looks like this, and so once again Dirac saves us, and you write this as an arbitrary function h times delta function, delta of this thing. Although for some reason I stuck in a minus sign, I don't really know why at this moment. anyway, so this delta function gives us a relation between k and omega. And in particular, it tells us that omega is id k squared. With dk squared positive, omega then is imaginary. So omega is the omega integral is actually a Laplace transform, the k integral is a Fourier transform. So our expression, our solution to this homogeneous equation for the diffusion of a density distribution of, say, molecules in a solution, or air pollution in the gas, is this, where this is the Fourier transform at time 0, say. And here this rho tilde is just this arbitrary function h of these 4 arguments. And now if we look at this at time 0, we see that rho of time 0 is just the Fourier transform of the density distribution at time 0. And so as an example, we can consider the case, suppose the density distribution started out at y. So at time 0, it was a delta function of x minus y. All the air pollution or all the bacteria were at x equal to y. Then rho at time 0 is delta x minus y, whose Fourier transform is this. Then rho tilde of k, of course, is just simply that. And so rho of time t is then, you take rho tilde, you stick it there, rho tilde is just that, stick it there, and you get this. So this gives you an expression for what the density distribution of time t is if you started out at time 0 with everything at y. And so this is the expression. This is a famous solution then of the diffusion equation. Notice there's a 1 over square root of t for each dimension of space, and then there's the square of the space distance, and then you divide by a t and a d and a 4. And then remember that this equation, this diffusion equation, is linear, so then you can generalize immediately. If you have a linear differential equation, you can add solutions. So you start adding solutions where at time 0 you had a little bit of y, a little bit of y prime, a little bit of y double prime. You integrate over y, an initial distribution. You use this expression to get you. So this is the general solution at time t of a solution that has diffused from a solution rho of y at time 0. All right, I think that's the end of chapter 4. I was going to start 5, and if you want, I will, but I imagine that you'd rather that I go back and discuss something else in more detail. You know, the more feedback you give me, the better I can teach you. If I don't know who you are or what you're thinking, it's hard for me to teach you. I'm teaching an abstract group of people, and it's hard to know how to talk to abstract people. Also, as I said to you in class, you know, if you ask questions, if you get in the habit of asking questions in class and out of class, you'll learn more as graduate students and as professional physicists. You'll just learn a lot more. And you might say, you might have learned from somebody else. Somebody else might have frightened you into thinking that if you ask a question, somebody will know how little you know. In fact, by and large, the professors know how little the students know. So don't worry, you're not going to give away anything if you ask a student a question. Is that a question?
Yeah, a couple times we're talking about an operator, like the differential
All right,
operator.
let me come close because
Oh, okay.
my hearing's not so great. What?
Okay, so there's a couple times where you use the differential operator, yes. And,
Yes.
I'm a little bit, I just wanted to make sure that I understood what's going on. So originally this is some polynomial or just some function of a derivative, right?
Yeah.
And then when you're doing Fourier transform on it, it's no longer a function of derivatives, it's a function of I and K.
Right,
where
right,
I is imaginary number.
because this thing is differentiating with respect to x,
Okay,
and the only x on the right-hand side is e to the I kx. Everything else is k.
okay,
So if you just differentiate e to the I kx, which is the easiest thing in the world to differentiate, it just pulls down a bunch of, it just turns p, every time there's a derivative, d by dx1 goes into ik1. The second derivative with respect to x2 goes into ik2 squared.
okay,
Okay, so that's what that is.
okay,
Do you want a candy or?
sure.
Okay.
All right, we got a couple of minutes for another question if. Of course, that explanation was a little too private, but I suppose you all heard me and so understood what I was saying. Anyway, let me actually tell you something for full disclosure. When I was an undergraduate, I always asked questions. And then in between being an undergraduate and a graduate student, I ran into some guy who had I think he had just gotten his PhD from Harvard. I think that was and we were talking, and he said to me, I asked him a question, and he said, oh, you're so lucky, you can ask, you're a student, or you're an undergraduate, or you're not yet a graduate student, and you can ask questions still, without appearing stupid. And he actually put the fear of asking questions into me, and so for years after that, I didn't ask as many questions as I should have. I mean, I asked some, but not as many as I would have if I hadn't talked with him. So, fear is one of the worst things. I mean, it's useful in some cases, of course, but, it helps you get out of houses that are burning on fire quickly. But apart from such situations, it's generally a downer. And so, trust me, ask questions. You will not be thought less of by faculty. In fact, you will be generally thought more of. You will be one of the students whom the faculty notice. The faculty will know your name, and they may wind up fighting over you as to which professor you'll do research with. That's my advice. All right, I think we're done. Why don't you press that red button and turn the thing